Looking into the night sky, we are often wowed with the expanding universe. Quantifying this vastness is quite useful as it's not really science unless you write it down. Now, it wouldn't make sense if someone came up to you and said, "Hey, did you know the mass of the sun is about 1.9885 times 10 to the 38 kilograms?" The typical response to that would be, who the hell starts a conversation like that? Things in the universe have mass. Some things might even have negative mass, but we'll leave that for sci-fi writers and theoretical physicists for now. These masses can range from very tiny to very, very massive. To not get swamped by giant numbers for every massive thing, we use solar mass units. The mass of our sun is 1 solar mass. Our Milky Way is about 1.15 times 10 to the 12th solar masses. My depression is just about 10 to the 30th solar masses. Obviously, numbers like that would look way worse when fully spelled out, though you don't really need to spell out that last one. Now, when it comes to distances, kilometers, or miles if you're of the imperial variety, won't exactly cut it when we're dealing with distances that are the equivalent of circumnavigating the Earth about 3,700 times in a little bit. That is actually 1 astronomical unit, the average distance of the Earth to the Sun. Still, astronomical units are not long enough when we're looking at distances to the nearest star or the width of a galaxy. For these large distances, we can also use light years, the distance light travels in 1 year. However, more academic works use parsec. A parsec is roughly 3.26 light years, or 1/12 of Hans Kessel run. If you were to define fully what a parsec is, let's say we pick a star that's on the polar axis of Earth's orbit. As we go through our orbit, that star will shift due to parallax. This shift depends on the distance d to the star. If the shift of the star as we observe it is 1 arcsecond, or 0.0028 degrees, then the distance that star is from our orbital plane is exactly 1 parsec, or 30.9 quadrillion meters. For context, a circle is made up of 360 degrees. Each degree is made up of a minute, each minute is made up of a second. For a somewhat well-known fun fact, if you want to estimate the angles when you're looking at the night sky, you can stick your thumb out at arm's length, and the width of your thumb will be just about 2 degrees. So for our star here that's 1 parsec away, this motion would look very, very tiny, or our thumb will look very, very massive relative to it. The math behind this is easy to explain, I think. Let's say the angular shift we observe is 1 arcsecond. The distance of the Earth to the Sun will take as 1 astronomical unit. The distance to the star will be d. Then Pythagoras and a small angle approximation will tell us that the angle is equal to 1 astronomical unit divided by d. Solve that for d and yeah, we get it. In units of parsec, we can have much smaller values when talking about the distance of the nearest star, or the thickness or diameter of our galaxy, or even the distance to the nearest galaxy. So I was just going to toss in 2 images here, one of our galaxy and another of Andromeda, and just put a line between the 2 of them. While proof checking the distance between the 2 of them, I realized we've actually done quite a bit of work looking into this galaxy. Messier 31 NGC 224, named Andromeda after the princess from Greek mythology and wife of Perseus. Like this image from 1888, taken by a Welsh businessman? What? And looking at recent years, well, this year, 2025, we've had this image, a massive mosaic from Hubble Space Telescope pieced together and released in January. And there's so much we can see from this one. The shape, the light, the spiral arms, its smaller companions. Like this bright star cloud, NGC 206, containing at least 300 stars brighter than most giant stars. These aren't exactly hospitable places for planet formation, maybe better suited for seeding new generation of stars in the future. And then they've highlighted these vast regions of dense star-forming clouds as well. Now, these are all about 2.5 million light years away, so what we're seeing right now happened at least 2.5 million years ago. Who knows what any part of Andromeda looks like right now? Could some regions have planets with strange and beautiful landscapes? Or star systems locked in wild orbital dances? Or maybe even someone or something looking back at us? It often saddens me that I'll never know. But I can keep imagining, keep living, working, make silly little internet videos and playing video games. It's years. We use years for the measurement of time. Well, we could use hours or seconds or days, but in a large scale stuff of the universe, things take a really long time to actually happen. And in the context of a human lifespan, we don't exactly have any event that will give us a standard to measure long periods of time. It's a lot easier to use years for these long periods of time. Like the sun, its age is about 4.6 billion years old, and it has about 5 billion years left until a fiery retirement party. Wait, that means the sun is in its young adult stage. Now, the reason we use numbers like these isn't just to make the numbers look nicer, though that is what they do. It's mainly about making calculations and comparisons more intuitive, within the context of space, not like on a bus or anything. People will look at you weirdly. Using the regular SI units, kilograms, meters, seconds, numbers can get absurdly large, or small, which makes them a pain to read, I hate that word, communicate, and sometimes even compute. So instead, we use units like parsecs, solar masses, years. This doesn't mean the physics changes, just that the scale of the units do. Now, let's say the gravitational constant can move from units of meters cubed per kilogram per second squared to parsec cubed per solar masses per year squared, simplifying the calculations. So now you're comparing star to star instead of stars to a watermelon or whatever we measure in kilograms.